Hi guys, this is Marco with Students Teach Orgo. Today we are going to go over peptide synthesis. First things first, we can't just spontaneously make a peptide bond. It's not that simple. And just as a quick refresher, the peptide bond refers to this carbon-nitrogen bond, particularly between two amino acids. So one way that we can go about making these bonds is with this coupling agent, DCC, and what that will do is it will take this carboxylic acid carbon, this amine nitrogen, and form a bond between them via a dehydration reaction. And so the dehydration is taking off this OH and one of the H's on this amine nitrogen here, and then that will produce a water molecule and that will leave the reaction. So what we end up with is this newly formed peptide bond here. So now to just look at this on kind of a bigger scale, with this peptide synthesis, now we have these two amino acids, kind of the two simplest ones, glycine and alanine. And when we react with DCC, what we'll get is peptide bond formation between this carbon on the glycine right here, so the carboxylic acid carbon, and the alanine nitrogen. And we get this product, which we label or we call glycine alanine, starting from the N terminus and then moving to the C terminus. So that's how we name amino acids or name peptides. We start with the amino acid sequence from the N terminus and then go to the C terminus. But there's a problem here. We can't, when we perform this reaction, we don't just get glycine alanine. We also get a whole host of other products as well, right? Because if you kind of have, you'll notice each amino acid has a free amine and a free carboxylic acid. So if you have these floating around in solution, it's completely possible that, this glycine will react with another glycine, right? This glycine's carboxylic acid, for example, could react with another glycine's amine, and then that will form glycine-glycine, like you see here. The same thing could happen with alanine, where it reacts with itself. Or you can even get kind of the reverse of the first product that we got, where the carboxylic acid on the alanine will react with the amine on the glycine, right? So you end up with this product here. And so this kind of poses a problem for us if we want to make a more selective reaction, if we want a specific product. So how do we go about getting that higher selectivity? And the answer is, we have two ways of doing it. The first one is this solution phase peptide synthesis. And the crux of this is really using a protecting group. So in this case, in the solution phase synthesis, we use this Bach as a protecting group. And just for your reference, this is kind of what the Bach looks like. This part over here to the left of the nitrogen, so that's the Bach group. So we can increase our selectivity by taking whichever amino acid we want first on the N terminus, reacting it with this Bach anhydride, so the Bach 2O, and then that will add the Bach group, as we see down here, onto our the nitrogen on the amino acid that we want on the N terminus, and then we can react this with whichever amino acid we want next in the chain. And you'll notice that now this amine group is kind of blocked up, right? It's protected by the Bach group, and so the only reaction that can happen now is the carboxylic acid on, in this case, this is glycine right here, that carboxylic acid reacting with alanine's nitrogen. And so we facilitate, again, the peptide bond formation by DCC, and then that will form this. And now we have kind of the peptide we want, but we still have this Bach group on here, so how can we get rid of that? If we react this with some kind of strong acid, like this one, for example, I believe this is trifluoroacetic acid, but other strong acids will do the same. It will cleave the Bach group off of the nitrogen, and then we have this here. And so we can now react this with DCC again, or react it with Bach again, and reprotect this amine, and we can grow the peptide that way. So that's one way to get a more selective peptide synthesis. One more thing about using Bach is that we must protect the side chain amine on lysine. So you'll notice here, this is lysine, this is another common amino acid, and this has two amine groups, right? It has the amine that's closer to the carboxylic acid carbon, which all of the amino acids have, but lysine also has this free amine out here in its side chain. And so in order to prevent side reactions with this amine and give us products that we don't want, we also protect that with Bach. And so that will add 2 Bach groups on either nitrogen. And now we can react this with some other kind of amino acid. The second more selective peptide synthesis that we use is this solid phase synthesis. Now there's kind of a double protection going on here. In the solution phase synthesis, we're kind of building peptides from, I'll just go back really quick to demonstrate. We're building amino acids from the N terminus to the C terminus, right? So we start with this glycine, and that's all the way on the left side on the N terminus, and then we can continually add amino acids on the right side and grow that C terminus out as far as we want. But for the solid phase synthesis, we're kind of going in reverse, where we're protecting the C terminus with some sort of solid phase. So usually it's some kind of polymer that's insoluble in solution. And from that C terminus, we're growing the amino acid to the left out towards the N terminus. And so in order to protect the N terminus of groups that we're adding to what we first have, we use this other protecting group, FMOC. And then this is kind of what the FMOC looks like. If you take away the chlorine, this is where the bond to the amine nitrogen would be. Okay, so now let's look at a more concrete example of this, because all of that explanation was kind of ethereal. So again, we're starting with glycine here, and say we want to have glycine on our C terminus this time. Okay, so we will begin by reacting it with FMOC, and the FMOC will protect the amine nitrogen on glycine, and then we can react our glycine with our solid phase, right? So usually this is, again, some kind of polymer with a reactive group like an alcohol or Cl out here, and then by using a coupling agent, we can facilitate formation of a bond between the carboxylic acid of this FMOC glycine complex thing and the solid phase. And so that will give us something that kind of looks like this, where now we have this ester here that's keeping the glycine attached to the solid phase. And then from there, we can go ahead and remove the FMOC group. This is done with piperidine, which is a base. And so this is a base labile group, and so that will take the FMOC off. And now we have this free amine group that we can now react new amino acids with. And to do that, we use another FMOC protected amino acid. So say we want to add alanine now to the N terminus. We use FMOC alanine, which we make the same way that we made this FMOC glycine. We just take free alanine and then add FMOC to it. And then using a coupling agent, that will facilitate peptide bond formation between the FMOC alanine, which is this part over here, and the free amine of the glycine that's bound to the solid phase. And one thing about this is now that we can kind of repeat this cycle where we take piperidine and we take off the FMOC group, and then we can react it with another FMOC protected amino acid, and then it will add another amino acid here, and then we could take that FMOC off and then repeat. So just like in the previous solution phase synthesis, you can grow out the amino acid chain or the peptide chain as long as you want. So this is kind of like a cyclic mechanism in that sense. Okay, so now we're going to move on not so much to peptide synthesis, but peptide analysis. One of the more common ways to analyze peptides is by complete hydrolysis. So if we take some sort of polypeptide and we treat it with 6 molar hydrochloric acid in solution for about a day, it will hydrolyze all of the peptide bonds in that polypeptide. And what we end up with is just the free amino acids on their own. And, this gives us a good idea about how much of each amino acid is in that, because, we can separate these things by chromatography, and that gives us, ideas of relative concentrations and things. But there's not much information conveyed about sequence through complete hydrolysis. So how do we determine sequence? Well, we use this process called the Edman degradation. And this is a lot more specific in that it will take off amino acids one at a time and allow us that way to determine peptide sequence. So this is the Edmond reagent down here, and this is what's used to facilitate the Edmond degradation. So let's take a look at the mechanism for that. Okay, so we begin with our peptide, and we can go ahead and start by adding the Edmond reagent, and it'll kind of shuffle things around over here on this end. It's not super important what happens, but the lone pair on the nitrogen attacks this carbon with 2 double bonds. One of those electron pairs from one of those double bonds, the one between the C and the N, will take one of the hydrogens from that nitrogen on the polypeptide, and then the electron pair from binding that hydrogen to the nitrogen will become the nitrogen's new lone pair. Again, not super important what's happening up here, but I thought I'd explain it. And that will add this group right here to the end. So this is kind of like a thiourea group. And from this point, now we can protonate with acid. That will protonate this oxygen right here, this doubly bonded oxygen, on that first amino acid in the chain. So again, I'm showing kind of 2 amino acids in this polypeptide chain. So this one right here, and then this one right here. And then the rest of the peptide chain kind of goes off that way. You can imagine going on for as long as you want. So then from this point, now the sulfur is going to attack this doubly bonded carbon right here. That will facilitate ring formation, and then ultimately it will get kicked off as a leaving group. And so what we're left with is this kind of ring here, and then our polypeptide chain, which is now 1 amino acid shorter, because this first amino acid in the chain, got broken off and became part of this ring, right? So you can kind of see the remnants of it right here. So those are the remnants of that first amino acid. And from this point, this will undergo a rearrangement and become this molecule right here, which we call a phenylthiohydantoin derivative. And these are kind of like amino acids, just free amino acids, in that we can separate them and identify what exactly they are by chromatography. So if you do this kind of reaction with a lot of the same polypeptide at once, then it will create a lot of the same PTH at once, and then that allows you to identify which amino acid was first in that chain. And from this point, we can take this shortened polypeptide chain, which is now 1 amino acid shorter, and we can repeat the process, and then that will take off this second amino acid group. And then that will give us its own PTH derivative, and then we can identify that one. So this we can also repeat multiple times in a cyclic kind of fashion, and determine the entire peptide sequence that way. Okay, so now we'll go into some practice problems. One thing I just want to mention before we start with this one, the Merrifield synthesis, that's just a fancy name for the solid phase synthesis, because it was developed by a guy named Merrifield. So this is a solid phase synthesis, so just be aware of that. But go ahead, you could pause the video and come back when you are ready. Okay, so for the solid phase synthesis, recall that we are building the peptide from the C terminus to the N terminus, so from right to left, basically. So that means the first thing we're going to do is use glutamic acid, then we're going to use valine, and then we're going to use isoleucine. So let's look at the mechanism for this. So again, we're starting with our glutamic acid, and the first thing that we want to do with the solid phase synthesis is attach that first amino acid on the C terminus to the solid phase, right, to that polymer. And so we do that first with FMOC. So we turn it into the FMOC glycine molecule over here. And then we can react this with the polymer, the solid phase, using a coupling agent like DCC. And then that will create this kind of ester-ish thing. All right, so now at this point, we want to make this reactive again so we can add the next amino acid closer to the N terminus onto this nitrogen right here. So we have to take off the FMOC protecting group. Again, we do that with piperidine, which is a base, so that will take the FMOC off. And then now we can add the next amino acid, which, if you recall, is valine. So Again, we're doing the solid phase peptide synthesis. We have to use the FMOC amino acid derivative. So we react this with FMOC valine, and we have to facilitate peptide bond formation with the coupling agent DCC. And so we go ahead and do that, and we get this. This is our next intermediate. And then again, we still have one more amino acid to add. So we need to make this end, the N-terminus, reactive again. We remove FMOC one more time, and then that gives us this. And then finally, we react with FMOC isoleucine to add it here. On the N-terminus is the last amino acid, and then we use DCC to facilitate that, and then we end up with this final intermediate here. And then the last thing that we have to do is just take off this FMOC group, which again we do with piperidine. So this is the solid phase synthesis. And again, this is with the piperidine, you're kind of just taking the FMOC off, and then you just react with acid at the end, and then that will take the synthesized peptide off of the polymer. So that will hydrolyze this ester right here. And then that gives you the final polypeptide, which is isoleucine, so this part here, valine, this part here, and glutamic acid, this part here. All right, problem 2. It's the same synthesis as the last question, just now we're using solution phase instead of solid phase. So go ahead, pause the video, and come back when you have a mechanism. Alright, so for the solution phase, instead of going C-terminus to N-terminus, now we're going N-terminus to C-terminus. So in this case, isoleucine is going to be the first amino acid that we work with, and then valine, and then glutamic acid. So now for the mechanism, we start with isoleucine, and when we're doing the solution phase synthesis, we want to use Bach as our protecting group. So we're going to react with Bach anhydride, and that introduces Bach onto this nitrogen. And then now we can react this with valine and DCC as our coupling agent, and then that will add valine to the C-terminus here, so we get this intermediate. And then now we can take this and react glutamic acid and DCC with this polypeptide. That will add the glutamic acid here. And then finally, we want to get rid of this Bach group because now we have the 3 amino acids in the order that we need. So we get rid of this Bach group by protonating it with some strong acid. Again, I have this trifluoroacetic acid here, and we just add that to solution, and then it will cleave the Bach group off, and we're left with our final product. Again, this is the same thing that we got in the first synthesis. All right, and then for problem 3, there's a lot of information here, so you might want to just read a bit closely, but come back when you're ready. Okay, so they tell us in the problem that complete hydrolysis of the oligopeptide gives us 3 alanine, 1 proline, and 1 tryptophan. So now we have ideas of kind of, the relative abundance, relative concentration of these amino acids, but we don't know what order that they come in, right? And that's where the Edmond degradation information comes in. They tell us that first, the first PTH derivative is tryptophan, and then the second one is proline. So this tells us that starting from the N-terminus, the first amino acid is tryptophan, and then proline, and then whatever comes after that can't be too certain just from the Edmond degradation, but we know from complete hydrolysis, right, after we get rid of tryptophan and we get rid of proline, there are 3 alanines left, right? So those must come at the end, and it doesn't matter the order because they're all the same. So what we end up getting from this, the sequence of the oligopeptide is tryptophan, proline, alanine, alanine, alanine. So this is our oligopeptide. Okay, and our last practice problem. Okay, looking at this, you should be able to identify that this is a solution phase synthesis. Generally speaking, right, we have this Bach group here, and then we have this second Bach group on this reagent over here. So this is solution phase synthesis. Let's go through the mechanism. We start with these 2 reactants, and the first reaction is introducing DCC. So that will facilitate peptide bond formation between this carboxylic acid carbon and this amine nitrogen. So we end up with this intermediate here now. This might be a little bit misleading, but this molecule just flips upside down during this, just so that the drawing is nice. The next reaction that they tell us is reaction with trifluoroacetic acid. So that will take off the Bach group from the N-terminus nitrogen, and we get this intermediate. And then the final reaction that they tell us is reaction with this new kind of peptide piece and DCC. So you'll notice that now on the intermediate that we got from the previous step, there is no protecting group on it anymore. But in this reagent, there's a Bach protecting group on its nitrogen. So that should tell you that now this is going to be our new N-terminus, if this is protected by Bach. So the carboxylic acid is going to react with the amine on the previous intermediate, form a peptide bond there, and then what we end up getting is this polypeptide. And notice that in the problem, let me just go back, they don't give you another step to remove Bach at the end, right? They don't have a second reaction with a strong acid like trifluoroacetic acid. So you just end up getting this peptide with the Bach protecting group still left on it. So hopefully that is clear.